This is my second video about the Stern-Gerlach-Experiment. The Stern-Gerlach-Experiment is an experiment that was used to demonstrate or is still used to demonstrate the quantization of the spin of electrons. If you don't know what I'm talking about right now, I really recommend watching the first video of this series. It will be linked in the description and it will also pop up on the screen right now. In this video, I will explain what this experiment is all about and what I'm trying to achieve. Now there's a change of plan. If you've seen my video about the new equipment I recently got, you know that I'm now the proud owner of a turbomolecular pump, and I decided to scrap the idea to use the cryo pump as my high vacuum pump, and I will use the turbomolecular pump. This is the rack I now built from the pieces I had used in the rack that held the cryo pump, and I now have to find a way to mount the turbomolecular pump to this base here. And it's one of those situations where you're at first a little bit disappointed or bummed that you have to scrap the idea you worked on for so long, but in the end it turns out that this solution is way better. The design of the rack allows me to mount a linear rail here, just like I talked about with the cryo pump. So I just finished assembling or testing the mechanism I thought of to swivel this end here where the detector sits. So if you remember, we have a potassium beam inside our tube here, and we want to measure the intensity at different locations, and for that reason we need to position the detector at different locations. And my idea was this one, where you just swivel it and I would have some gears here or another mechanism to move it at this end, which means the detector would move too. The problem is that the positioning here has to be very precise, and I don't know if you can hear it, but there's play in there. You can't get around that because you need some space between the aluminum extrusion and your 3D printed part. And just as I assembled it, I realized that it's way easier to mount some more aluminum extrusions here and use a linear rail with a stepper motor that is fixed right here to just move this tube from left to right. So I think that's the way I'm going to go, because this method won't work. And the tube will go just like this. You will see it in future videos or even this video. And yeah, all in all, this is the way better solution, and I'm glad that I decided to change it. I now have to find a way, as I said, to mount the turbomolecular pump. There is no obvious way to mount this. I don't see any mounting points. There is a little bit of space up here where the cable is now located, and I could design a clamp. I have to 3D print it. I can't machine any metal. I don't have access to a metal workshop. Or I could just use the KF40 flange on top here to mount it, and that's what I decided to do. I may add another additional clamp down here. I haven't decided that. And the pump will be located beneath this aluminum bracket right here. I just used a scrap piece of aluminum that I had laying around and drilled a large hole into it, because I want to use this T-piece to fit it right there so the turbomolecular pump can mount at the bottom here. And to do that, I 3D printed these two parts. One viewer asked me if I could talk a little bit about my 3D printer setup, but honestly there's not that much to talk about. It's just a standard Ender 3v2 printer. I didn't modify it, I just added the silent fan upgrade, so these are Noctua fans, and I also added these fans for the power supply, so it's for the motherboard and the power supply. So the printer is a little bit more quiet, because at the beginning I had it running next to my bed, and now I placed it right in front of my bathroom. I just have a one-room apartment, so my space is limited. And yeah, I'm not the kind of person that likes to tinker with its 3D printer a lot. It's just a tool for me, and I just want it to work. I totally understand if people like to work on their printers and modify them and make the craziest stuff with it. But for me, I don't have the time for it. I have other projects I'm working on, and I don't have the money for it. So yeah, it's just a tool for me. So I 3D printed these two parts here. Whenever I'm printing parts that are need to withstand some force or need to be stronger, I most of the time increase the wall thickness. This is printed with 2.4 millimeters wall thickness. The standard value is 0.8. And the infill is a little bit higher. I think it's 30% in these cases, but most of the strength from a 3D print comes from the thickness of the walls. So that's the main value you want to change if you need a stronger part. I also added these threaded inserts here if I want to clamp it additionally from the bottom. But you will see in a second what these parts are for. These parts act as a bracket to hold this T-piece here. I can just slide it in them. It's a little bit tight, but I want it to be. So they are just two shells that clamp around the T-piece here. The other one goes on just like that. Let me quickly use a clamp to push them together. Just like that. And I will heat insert hex nuts right here, so I can use screws that go through there to keep them in place permanently. Now that both halves are clamped together, there's no way they're coming apart. I can use this little edge or this ledge here and this hole here to align it and push it in the hole. And now I can mark these screw holes here to the aluminum plate, drill in the aluminum plate, get some threads in there, and then I can screw this assembly here to this aluminum plate. Okay, I have now drilled these 6 holes that I can use to mount my 3D printed bracket to. Okay, the bracket is now installed and it is plenty strong to keep everything in place. The only problem I see is that I can't really bake out the system, at least not this T-piece here, because the PLA will soften at, I think, 60 degrees Celsius. So this is something I have to think about and see if it's possible without baking out the system, or at some point maybe replace this with a more heat resistant polymer that I can 3D print. Yeah, but at this point in time, that's the best I can do. And now let's mount the turbomolecular pump to the bottom. So the turbomolecular pump has been mounted to the KF flange and it is plenty strong. I don't think I need a second clamp around here. If you are familiar with turbomolecular pumps and you know, or if you think I should put a second clamp around here and get a second aluminum extrusion here and mount it to the pump, let me know. This is my first time working with them, but I have seen them being clamped just at the KF flange, so I think it's okay. It's really solid. And as you can see, the controller for the pump will be mounted here. I designed a bracket that goes around there and around the back to hold it in place. I have to 3D print it. I ran out of filament, so I have to order some. And then the controller is permanently fixed to the rack where all the experiment takes place. In case you don't remember or you don't know what this is all for, I recommend watching my first video about the Stern-Gerlach-Experiment, where I explain what my goal is and how I plan to demonstrate quantum effects at home. Basically, I will mount this piece to this T-piece right here, and as you can see, there's a flexible stainless steel hose here, and I will mount a linear rail with a stepper motor right here, which allows me to manipulate this tube right here and swivel it back and forth, so I can scan the area and see where the atom beam is. On the other side right here there will be an atomic beam furnace which produces a beam of potassium atoms, which I will detect with the detector that sits right here. And yeah, this is something for a future video because I need somebody to machine the detector or some parts for the detector and for the atomic beam furnace for me, because they have to be out of stainless steel or steel. I'm currently talking with somebody who offered to do that for me, so I'm very grateful for those persons that spent their time to help me with these projects. As soon as I have the money to buy a linear rail with a stepper motor to mount here, I will do that. I can't wait to get this working, at least in a way that I can detect the atom beam. The magnet assembly, this will be far in the future because it's a lot harder to machine than the atomic beam furnace or the detector. Yeah, what I'm going to do now is to test if the turbomolecular pump runs good as it is here, and I will use my ionization vacuum gauge to measure the vacuum level. Okay, I have everything connected. You can see the ionization vacuum gauge right here. This piece here has no function, it's just flopping around. I just want to test if these connections here are also vacuum tight. You can see the turbomolecular pump, the controller for the turbomolecular pump. The 4-line vacuum pressure is shown right here. And my roughing pump sits on this chair right there, because I want to further test if it's the vibrations of the 4-line pump that causes the turbomolecular pump to make the weird noises it did last time. So I'm now going to lower the pressure by using my roughing pump, and after that I'm going to turn on the turbomolecular pump. Quick addition, I forgot to add the vacuum valve right here, so I did that, and I also used a clamp to clamp down the hose right here, so any vibrations that propagate through the stainless steel hose here won't reach the pump. Let's start the turbomolecular pump. The noise you hear right now is just coil whining from the controller here. It's not the pump itself. Let's just hope the pump stays as silent as it is now. Okay, the pump is up to speed. Let's turn on the ionization vacuum gauge. So the pump does not make the noises you heard in my last video, the video called "My Turbomolecular Pump Makes Weird Noises." There you can hear something, because this is my first turbomolecular pump. I have no comparison to how loud these should be, but yeah, it sounds like it will work for quite a while. Maybe it's just the motor, maybe it's a bearing. The most common theory was that it's a failing bearing. It could be possible. This pump was serviced in 2010, it looks like, by the sticker right here. But it doesn't sound roaring, if that describes it. If I heard it and somebody told me it's a normal noise, I would believe them. So that's good news. So while this is pumping down, let me show you my plans for the detector and the atomic beam furnace. Let me first show you the atomic beam furnace. This is the main part of the atomic beam furnace. As you can see, this is a KF40 flange, and this is the high vacuum side. So everything on this side will be at atmospheric pressure. And if we look at it with a cut, you can see that there's a chamber inside this piece, and this chamber is open to the high vacuum. And this is where the potassium will be stored in. And then I can heat the cylinder from the outside, this part right here. This thread is just for a temperature sensor to be mounted to. And by heating it, the potassium inside this chamber will be heated until it vaporizes and gives off atoms. And then there is a second part, this part right here, that mounts to the flange on the high vacuum side. And you can see that there is a space right here, and this will be used to put in some capillary tubes from some medical cannulas to collimate the atomic beam. And then there's just a lid that goes on top, so the capillary tubes are held in place. So after this part here, I have a beam of potassium atoms that is collimated, but as you know, I need a potassium beam that is a slit or a thin line. So I have these pieces here. These are just some threaded rods that thread into the piece right here. And here at this location, they are designed to hold a optical slit. It's a slit made for spectroscopy and other experiments. It's the only slit I found that has a 200 micrometer, I think, slit. And this is basically the aperture that forms the atomic beam in a narrow line. I am currently talking to somebody who said he would be able to machine this, and I'm very thankful for those persons, and let's just hope everything works out and this design works out. I copied it from a paper I found, a paper that described a simple atomic beam furnace, and yeah, let's hope this design works. And this is the part that I designed for the detector. I will go into detail how the atomic beam furnace and also the detector works. This is a Langmuir-Taylor detector, and it's just a preview for you to see what is coming next. This basically has to be machined out of metal because it's in the high vacuum, so any polymer, okay, I could use PTFE, Teflon, or maybe PEEK, but I think it's easiest to machine it out of metal. And this will basically sit on a high vacuum feed-through, and this is a nickel shield that will catch the electrons that are emitted by the tungsten wire that is spanned across these two pieces here. Yeah, as I said, I will explain the function of the detector when I have all the parts and I can show it to you. This is the high vacuum feed-through. It's just a KF40 flange with several wires that are sealed vacuum tight. I think these are metal to glass seals here, and these are made for high vacuum applications. And it has this ceramic piece here that fits onto these wires like that, and I can push it on, and it's a pretty tight fit, so it doesn't move on its own. And the piece you just saw in Fusion 360, I 3D printed it, and it basically fits on it like that. And I can use a M4 screw to screw it down through this hole here. That's why there is the rod in the middle with a thread. So I can put a screw in here to fix it. And then the side openings here are made for the wires to go through. And then on the top here there will be the shield that is mounted to it and the holder for the tungsten wire. As this is machined out of metal, I will have to use some PTFE pieces to insulate the metal parts from each other, because of course there will be a different potential. But I think that's not that big of a deal. I will also need some PTFE screws or PEEK screws. They are very expensive, I saw, but I think it's the only way. I will ask the person if it's possible to machine it out of PTFE. There won't be any temperature problems, but yeah, this is the plan for the future. I just wanted to show it you as a kind of preview. The pump has now been running for about half an hour, and I started to hear this sound again. It's just occasionally, I don't know if it's when the pump accelerates, but it's not nearly as frequent as I heard it before. I really hoped it would be the vibration of the roughing pump that caused this, or maybe the pump, the turbomolecular pump, just stood for a while and needed to, I don't know, run for a while to lubricate itself. But you can hear it whining occasionally. So it seems there is a permanent, I don't know if you can hear it, it seems like there's a permanent problem there. I really hope it lasts long enough for this experiment to work. At some point I may have to attempt to switch the bearings inside. I read that that's really hard. There is a guy on YouTube, Glasinger is his name, or Glasinger, I don't know how to pronounce it. I really like his videos, and he had a video about a turbomolecular pump he repaired, and he just used skateboard bearings. There were different opinions about that. Some said that they are not nearly as capable as the bearings inside those pumps, and I believe that. The speeds a turbomolecular pump is running at is just crazy, 75,000 RPM. So I'm a little bit hesitant to do that, so as long as it works, I will use it. At some point I may try to find some high-speed bearings or high-precision bearings that I can use to replace the ones inside. But as long as it's this small of a problem and it's only occasionally, I won't risk opening this pump and maybe never getting it to work again properly. So yeah, the pressure is down to 1.3 times 10 to the power of minus 5 torr. I need to get down to 4 times 10 to the power of minus 6 millibars. I think I can do that if I bake out the system. As some people mentioned in my last video, it's basically water vapor or water that is absorbed to the walls here. And I heated it with a heat gun and saw the pressure rise dramatically. The only problem, as I said before, is this 3D printed part right here that's not resistant to temperature. Maybe I can get around it by heating this here slowly, and then yeah, we will see about that. I don't know if you can hear it, but sometimes it makes that noise. And yeah, I'm glad that it works the way it does right now. I'm pretty happy about the design. As I said, I can use this here to swivel it, and this is the perfect location to mount a linear rail and a linear motor. And yeah, I think that's everything for today's video. I again want to thank the person that gave me this turbomolecular pump for very little money. Even if it doesn't work properly, it's still absolutely worth the money I paid for it. And yeah, thank you a lot for watching. Okay, quick addition. I disconnected the tube here just out of convenience and pumped down the whole system again. And this time the turbomolecular pump doesn't make any noises at all. So I feel like it might be that the pump just had to run for a while. Because it's gotten better every time I started it up. The first time I heard a lot of noise, the second time, the one you saw in the video before, it made noises occasionally, and now it's completely silent. And I even have the roughing pump on my desk, so the vibrations do not seem to be the problem. And I'm also getting pretty low pressures. I'm currently at 4.9 times 10 to the power of minus 6 torr, and it's still falling, so it seems like I can get in the range I need for the Stern-Gerlach experiment without me heating the system to desorb any water on the walls. So those are pretty good news. And I also got new filament, so I'm currently printing the bracket I will use to mount the controller unit here. Yeah, I just wanted to tell you this, because I'm pretty happy that the pump seems to be in relatively good shape. Thank you a lot for watching.